The last topic we're going to cover in this unit on radicals is graphing radical functions. But before getting to that, let's just refresh what we're going to do, which is we did before the break, which was solving radical equations. So just to refresh, we want to solve radical 4x plus 7 equals 3. You might recall the objective here is to get the radical by itself. So I'm going to subtract 7 from both sides. Radical 4x, that's a little messy there. Radical 4x equals negative 4. We squared both sides. 4x equals 16. X is 4. And then remember, we had to go back and check. And when we put in 4 for x, we get radical 16 plus 7 equals 3. 4 plus 7 does not equal 3, so there's no solution. And you could have seen that right away because when you set the radical or got the radical by itself, it was set equal to a negative number, which we know is not possible. Now, a square root function, let me just give me some room here, is a function containing a square root with the independent variable in the radicand. Now, like most of our graphing, we're going to be using our graphing calculator to do this for us as much as possible. Okay. And what we want to do is similar to what we did when we did absolute value functions. Okay, because technically these are the inverse of an absolute value function. What we want to do is see what happens to our base case, which is y equals the square root of x. And when we make changes to that equation or that function, and then we also want to identify the domain and range. So if I want to graph the equation y equals the square root of x, let's just pull up our graphing calculator here. Now, in this particular calculator, to get the square root symbol here, it's second the x squared button, and then I put the x in there. And then, like all of our graphing, we want to call up the table as opposed to looking at the graph itself. Now, you'll notice, and this is the key thing, is that you're getting error messages for certain values. That means those are values that will not be able to exist for x. So if we go back to, and what we want to do is choose those values that are going to give us nice numbers as much as possible. So if I go back to the graph here, if I were to graph this function, okay, when I put in 0 for x, I get 0 for y, 1 for x, 1 for y, 4 for x, 2 for y, and 9 for x, 3 for y. Okay, I could put in the 2 and the 3 for x and get 1.4, 1.7, but let's use actual integer values. And you'll see that it is a curved figure, like so. And we don't put an arrow at the 0, 0 because I cannot go beyond 0 or a value smaller than 0 for my x values. Okay? And we're going to get to the domain and the range in a couple of minutes. So now, let's see what happens when I add 2 to this function. And again, you would be putting this into your calculator, and you'll see that when x is 0, y is 2. When x is 1, y is 3. When x is 4, y is 4, and 9 and 5. And it's a little too high. 3, 4, and 5. And hopefully you've noticed what's happened here is that your graph shifted up 2 units. So our conclusion is for any positive number k, graphing y equals the absolute value of x plus k translates, okay, or shifts the graph of y equals the absolute value of x up k units. Okay. Conversely, for any negative number k, graphing y equals the absolute value of x minus k translates the graph down k units. Okay. So what we want you to realize is that there is a translation going on here. All right. Remember, translation is a shift or slide of the original figure. So that if it's outside, if the value is outside the radical, okay, then we're going up and down. So you should then be saying to yourself, what happens if it goes inside the radical? And when I do this, what you'll see happen here is -3, 0, -2, 1, 1, 2, 6, 3. So now hopefully you're seeing that what happened is for any positive number k, y equals the absolute value of x plus k, where k is now under the radical, shifts it k units left and y equals x minus k shifts it k units right. Okay. Similar to what we saw with the absolute value functions. Okay. Now, what is the domain of a function? All right. Well, if you might remember, the domain is the set of inputs or x values. Okay. Are there any restrictions on the domain of a square root function? Yes. The radicand cannot be negative. Okay. That's what we saw, for example, when we did the do now. So to determine the domain of a square root function, what do? We set the radicand without the square root symbol greater than or equal to 0 and solve. Okay, so what is the domain and range of the function y equals 2 radical 3x minus 9? What I do is I set the 3x minus 9 greater than or equal to 0 and solve. So my domain is x is greater than or equal to 3. Now, the range are the y values that go with it. So my range is, in this case, the corresponding y value when I put 3 in for x, which is in this case is going to be 0. Okay? And that's how we can identify the domain and range. All right, so that is how we deal with and graph absolute value functions.